So today we're going to talk about non-steady state well equations. The other day we talked about the steady state equations, and we talked about them for both confined and unconfined conditions, and we're going to do the same today. So the first is for the confined condition. We have the Tice equation, which is S, the drawdown, equals h sub 0 minus h, and that's equal to q over 4 pi t multiplied by w of u. Now this big capital W of u is called the well function, and it's a dimensionless parameter that's actually the result of an integral, and you have to look it up in a table or do the infinite series for it, which is shown down here. So this is a function of something called u, which is also a dimensionless parameter, and u is defined as r squared s over 4t t, where r is the radial distance from the pumping well that you want to know what the drawdown is. S is the storativity of the aquifer, which we defined a couple lectures ago in the aquifer properties lecture. And then capital T is the transmissivity, and T is the time since pumping began. It can be in days or hours, usually it's in days. So again, if you want to know at a certain point what is the drawdown at a certain time, you can plug that into U and then look up or calculate the infinite series, but looking it up is a little bit easier, the value of the well function W of U, and calculate what the drawdown is. Okay, so there's a table in your book, which is table 6.5.1, that shows, and that's shown down here at the bottom, the values of W of U for various values of U. And the table's a little weird to read, but across the top is, like, for example, if you had a U value that was like 2 times 10 to the negative 6th, you would go across the top to find the value of 2, which is right here, times 10 to the negative 6, that's right here, and your value for W of U would be 12.55. Okay. So we're going to do an example problem in a minute where we'll apply this and you can see how it works. But in essence, it's similar to the steady state well equations, but we have this W of U, this well function that we can define a value for different times and distances away from the pumping well. For the unconfined case, we have something called Newman's solution. Newman's solution looks somewhat similar. Again, so S, the drawdown, is equal to h sub 0 minus h, which is q over 4 pi t times a different function, also a well function, but this one is not just a function of one parameter, but of 3 parameters, ua, ub, and this guy. So for this one, instead of looking it up in a table in your book, there's a figure 6.6.2, which is also difficult to read. But first you would calculate the value of u sub a, which is exactly the same as u from the Tice equation. Also u sub b, which includes the specific yield parameter here, which was not in the Tice equation, and then this other parameter over here. You calculate the values of all of those, and then you can use this figure to calculate the value of the well function, just like you would use the table in the Tice equation. Now the good news for you is we're not going to do anything with Newman's solution in the class. We're not going to do any example problems, homework problems, test problems with that, but I just wanted to show you that both these equations are similarly structured and they exist. We will just do an example and a homework problem on the Tice equation so you can see how that works. Okay, so the example problem, we have a confined aquifer. Transmissivity is 10,000 gallons per day per foot. S, the storativity, is 10 to the minus fourth. The flow rate from the well, Q, is 1,000 gallons per minute. And we want to know what is the drawdown at a distance of 1,000 feet, 2,693 minutes after starting pumping. Okay, so that's the problem. We're in a confined aquifer here. We know it's not steady state because we're asked about some time after we started pumping. So we're going to use TICE. And when we use TICE, we need to start with calculating a value of U. U is equal to R squared S over 4TT. So R is 1,000 feet, square that, times the storativity, 10 to the minus fourth, divided by 4 times the transmissivity, 10,000 gallons per day foot, multiplied by the time, which is 2,693 minutes. And we just need to do a little unit conversions. This U is a dimensionless parameter, and we have storativity up here, the 10 to the minus fourth is also dimensionless, so we have foot squared in the top, so we need foot squared in the bottom. This gallons we need to convert into feet cubed, and the days we need to convert into minutes. So we have 1 day is 1440 minutes, and then we have 1 cubic foot is 7.48 gallons. And if we do that, we'll see that this the units here go to dimensionless for U. And the result of that is we get 1 times 10 to the negative second for the value of U. Now we would go to table 6.5.1 in our textbook and look up the value of 1 times 10 to the negative second in that table to find the value of W of U. And when we do that, we get W of U is equal to 4.04. You can go to your table in your book and look at where I got that from now if you'd like. Now we can plug it back into TICE. S is the drawdown, Q over 4 pi T, W of U equals 1,000 gallons per minute. We're gonna, let's see, divided by 4 pi T, 10,000 gallons per day foot. So we need to do a unit conversion here since we have minutes on the top and days on the bottom. So we'll multiply up here by 1440 minutes per day. And then we're going to multiply the whole thing by 4.04, the well function that we already looked up. And if we do that, we get a result that the drawdown at that time, at that location, is 46.3 feet. So this is a very powerful equation that can be used in a lot of different circumstances. One of the more common places I've seen it used is in a dewatering situation for construction, where time is usually a precious resource and a well needs to be drilled and pumped in order to lower the groundwater table so construction can occur. They want to know how long do we need to pump before the site is dry. So how far in advance of construction do we need to drill the well and start it pumping in order to do that? This would be the equation you'd use for that. And then I wanted to just talk a little bit about well tests. So one of the places that engineers interact with wells a lot is in testing and the results of tests. Aquifer, there's 3 kinds of tests I've listed here: aquifer tests, slug tests, and one that I call specific capacity testing. And these all have different purposes. Aquifer tests are most commonly done by geologists or hydrogeologists, and they're used to measure aquifer parameters like transmissivity or hydraulic conductivity. They tend to be long tests that are a little bit more expensive to do, where you basically pump water from a well and observe the rate and extent of decline in groundwater levels in nearby observation wells. We did some example problems in the steady state portion where we did essentially that. We looked at pumping from one well, response in another, and we calculated things like transmissivity from that. A much cheaper, more common test that's done is called a slug test, where the slug is a slug of water or a slug of mass is either suddenly removed or added to the well casing. So a common way is like you take a long slug that's a couple of feet long that fits inside the well and just drop it down the well on a big string or rope. And when it plunges itself into the water, it's going to sort of instantaneously raise the level of the water in the well as that mass displaces some volume of water in the well. So the water level suddenly rises in the well, but the surrounding groundwater table is not that high. And so once the water rises in the well, it's going to start seeping out of the well back into the aquifer. And as it does that, the water level drops. And that water level is, that drop of the water level, the rate that it's happening, is observed over time. And you can gather parameters like transmissivity from that as well. And this can be useful at like a hazardous waste site where you don't want to pump water out of the well, but you still need to measure some of the parameters in the subsurface. The last kind of test is I call it specific capacity. Most people would just call it a pump test or a well test. After a well is drilled, all wells are tested. And typically what's done is you've got a pump in the well, you pump it, you measure the flow rate that the pump is achieving, and you pump it for a long time and determine what the maximum drawdown in that well is for that flow rate. And you relate somehow from just that well the flow rate to the maximum drawdown. And there's a lot of sort of empirical relationships and rules of thumb and things that have been developed to determine things like transmissivity just from that, even though there's no theoretical relationship or like well-established relationship that's available in all cases for that kind of a test. So this wraps up our talk about groundwater and flow to wells. We talked about aquifer properties, groundwater flow in general, steady state flow equations, as well as non-steady state flow to wells.